Hello everyone, this is Amrita Dasim and we are here to present and discuss the paper Robust Optimal Depth Control of Hovering Autonomous Underwater Vehicle, which is a research work by Y.S. Song and M.R. Arshad. To get started, as the name suggests, the study focuses on depth control of a HAUV, which is generally used to inspect any kind of structural issues on a ship's hull, including cargo ships, cruise ships, or even oil and gas offshore platforms. It is also used for seafloor observations, for port and harbor security, or for other archaeological and research purposes. However, the HAUV control problem is quite challenging due to the disturbances and uncertainties in the underwater world. Besides, the mathematical model of an HAUV system described by hydrodynamic parameters including added mass, damping and buoyancy forces, and other external disturbances and model nonlinearities are difficult to precisely characterize and simulate. This requires to study efficient control techniques that are less complex and computer intensive, which further allows for real-time onboard application of the control algorithm. With this motivation, this paper presents a robust optimal control method that uses a combination of robust filter control and optimal control techniques for station keeping of a HAUV. To give a brief overview, the authors use optimal control to minimize the tracking error of a dynamic system, whereas robust control is used to compensate the hydrodynamic effects, model nonlinearities, and other external disturbances. Further, the authors compare the proposed method with sliding mode control, which is discussed in detail later in the presentation. In this paper, the HAV system is represented by equation 1, which is a 1 degree of freedom nonlinear dynamic equation in the vertical direction. Here, Z represents depth of the HAUV, MRB is rigid body mass, MA is added mass, DL and DQ are linear and quadratic dynamic damping coefficients, G is the net buoyancy force, tau denotes the thrust force, and W represents the external disturbance. The external disturbance considered in the paper was the wave disturbance defined as a sinusoidal force acting on the system in the downward direction, and this is formulated in equation 2. The wave frequency and amplitude considered for the external disturbance were 0.1 Hz and 5 newtons respectively. Further, for simulation purposes, parameters of an open-frame box-shaped HAUV were used, which was developed by Underwater Control and Robotics Group. The considered HAUV prototype is slightly positive Fitz buoyant and is controllable in the downward direction by using two vertical thrusters. Further, this paper only considers the parameters in the downward direction for all the simulations. Coming to the methodology, as mentioned before, the authors compared the proposed controller with sliding mode control or SMC. To give a brief overview, SMC is one of the existing robust control techniques whose control strategy is to drive the system states towards a particular surface in the state space, known as the sliding surface. Once the sliding surface is reached, SMC keeps the states on its close neighborhood. However, the disadvantage of SMC is the chattering effect due to high switching gains, which is caused by a zigzag motion of the error trajectory when it repeatedly crosses the sliding surface. This effect results in high wear of mechanical parts and degrades the performance of the system. To reduce this effect, smoothing functions such as saturation functions and hyperbolic tangent functions are used, but these only guarantee convergence of the tracking error to the close neighborhood of the defined sliding surface, but not the reduction of high-frequency fluctuations in most cases. In this paper, as a smoothing function for the simulations, the authors use a boundary layer saturation function with boundary layer thickness of 0.01. So that was a brief overview of SMC. Here now is Adik Shah, my team member, to continue this discussion further.
In this paper, the proposed design uses robust optimal control law. Firstly, the author rearranges the HAUV model represented in equation 1. Next, an artificial signal named equivalent disturbance is created to represent the effect of added mass, hydrodynamic damping force, external disturbances, buoyancy force, and model nonlinearities on the system, which is shown in equation 3, the Q. The figure represents a block diagram of a proposed robust optimal controller, which consists of two loops. The first one is your inner loop, which represents robust control loop, the blue box, which uses robust filler control technique to compensate the effect of equivalent disturbance on the system. The control signal is given by the robust filter controller called robust compensating signal UR. The second outer loop represents optimal control loop, that is the red box, which uses optimal control technique to inject a predefined error dynamic, which has the minimum performance index in terms of tracking error, into the system. The control signal is given by the optimal controller called optimal controller UO. Equivalent disturbances in robust control involves second-order derivatives in the mathematical model. To remove those derivatives, a low-pass filter needs to be added to the equations. One cannot measure the defined equivalent disturbance directly since it is an artificial signal. The optimal control signal is designed by assuming that the robust compensator can cancel the effect of equivalent disturbance completely. As a result, we get the dynamic of the tracking error. To get the error dynamic optimum in terms of the tracking error, parameters like Kp and Kd are designed. An error squared performance index J is shown in equation 9, where P is a symmetric matrix. The parameters Kp and Kd are chosen according to the values of maximum thrust and upper bound of tracking error. By using the performance index and the derivative of performance index with respect to Kd, the parameter Kd is adjusted so that the value of performance index is minimum. Coming to the simulations, all simulations are performed in Simulink to verify that the station keeping performance of the proposed controller is in the presence of initial tracking error and the wave disturbance. The defined desired path, initial value of the tracking error, and the initial value of the derivative of the tracking error of HAUV is shown in the table below. The proposed controller must bring the HAUV from the water surface to the desired depth of 1 meter in the presence of the wave disturbances. The values of the proposed controller used in simulation is shown in the table, and then the value of the defined error squared PI is achieved to be 2.11. Comparing it to the SMC controller, the value of the control parameters of SMC controller are also shown in the table, which has an estimation error of 20% with the MNC's parameters. Talking about the simulation results, the first figure shows the depth response for both the controllers. Generally, they achieve a satisfied station keeping performance. Settling time is equaling to 10 seconds while the tracking error is converged to 0. Proposed controller performs better than the SMC as compared, even with a 15% overshoot in response of the tracking error and the NR squared performance index. Second figure shows the tracking error of the proposed controller bounded within a small value of 0.002 meter, even with the presence of the wave disturbance. Thus, the proposed controller is able to compensate the effect of added masses, like buoyancy and external forces. The last figure shows the force profile for the two controllers in comparison. The frequency is 0.1 Hz and the maximum force of the proposed controller is 30 newtons. Although, altogether, it shows that they generate unnecessarily large control signal. In conclusion, the proposed controller combined the optimal control technique and the robust filter control technique. After the review of simulation result, it looks like the pros of the proposed controller method requires no hydrodynamic information of the HAUV system, which makes it very easy to implement it. Secondly, 0.1 Hz frequency of the control signal makes it suitable for the real-time application. The only drawback is that it generates unnecessarily large control signal for large tracking errors, and this can be solved in the future work. Thank you so much.